Good evening, everyone. Tonight we are going to cover merge conflicts with respect to GitHub and constant functions. I did want to give credit to Dr. Kevin Wortman for the use of his slides. I greatly appreciate that. For the agenda this week, we have a lab 12 for the Monday session. If you have a Monday session, you need to work on Lab 12. And then any of the other sessions, Tuesday through Thursday, those will be review sessions. Also, the portfolio is due for the 120 lab sections. That's due on Wednesday, December 11th. And final exam is next week. Our class, Monday, December 16th at 5 p.m. is our scheduled time for our exam. As far as question and answers, since I'm not there tonight, if anybody does have any, please send me an email and I will respond to those as quick as I can. Other than that, please come prepared on Wednesday to do our final review session. So on our merge conflicts, we're going to just do a quick review on Git and GitHub. It's a source code control. It's a tool used for programmers to share, track the source code, keep it up to date. Git is a general term. It's a popular source code control shell program. It's installed with Ubuntu, and you can use it as it is or integrate with a Git cloud offering. We're using GitHub. There are several other ones out there. GitHub is the one that we're using this semester, and it's a cloud Git service, and it just really facilitates that sharing of code with others all around the world since it's in the cloud. Repository is a term you'll see in the Git environment, and that basically holds a project. Some examples of that are Chromium, or maybe the Chrome history client.cc. Those might all be in a repository. And Lab 2 and subsequent labs after that all use a Git repository. So when you're pushing your code up to Git, it ends up in a repository and it stays there in the cloud. So just a quick review of the GitHub workflow. So the Git understands that a repository can be copied into multiple places all at the same time. If we look at just a single developer workflow, it might look something like this. So the user would start off creating a remote copy of the repository, and this resides in the cloud. That's where it's stored. When they want to make edits to it, they might clone it or make a local copy onto your computer. Do those edits, adding, committing, that's all done incrementally, and it's good practice to just add and commit periodically. That way you can roll back if there's errors. It's a good way to even track the code locally. When you're ready to save it back up to the cloud, you execute that push command. And that pushes whatever is at that local copy back up to the cloud, the remote copy. All right, so that's one user. What happens when we have multiple developers trying to use the code and syncing? That's where we start to see the merging conflicts. So Git isn't intended for large teams. The challenge is synchronization. And what if we have two users, maybe Alice and Bob, and they're working on, their assignments, and they both clone copies from the cloud, right? So Alice clones a copy, Bob clones a copy. Nothing wrong with that. But then Alice changes a file, maybe the main.ccc, makes an edit to it, and Bob changes the same file and makes an edit to it in a different spot. Alice will push the code, And when Bob goes to push the code, it will recognize that there are conflicts. And so the question is, which is the right version, right? Which one wins? And there's no right answer to that. The Git's not going to solve it for you. It's basically going to highlight the conflicts, and it's up to you as the programmer to make the determination which is the correct one. All right, so polling and merging conflicts. Just the Git rule is if your repository is behind, you have to either pull the remote changes, resolve the conflicts, and then push it back to the cloud, right? So do a pull, resolve the conflicts, push it back. The suggestion is avoid this at first. Use one account, one computer at a time. If you are in a situation where you're, pulling the copy to both to separate computers, you just have to be aware of it and communicate really between the programmers. That's the best way to do it. So let's look at an example here on a couple of different computers and how the conflicts occur. So if we have computer A and we do a clone, so here's our starting point out in the cloud. We have a repository that we've just built or we've been working on, and we come along a year later and we want to do some more work. So we do a clone to computer A. User A is going to work on that, and then also a clone to computer B. Doesn't matter what order those are in, but the bottom line is right after those clones, all three of these, the cloud, A and B, are all at the same state, right? Then computer A goes in, does some editing on the files, does the add, commit, and push back to the cloud. So far, nothing wrong with that. Now, the cloud and computer A are the same, but then computer B comes along and does some editing on the files. They never pulled this down, right? They're still working off of the original code that was in the cloud at the same time they cloned them together at, about the same time. So they're working off a different version. They're making edits to it, and then they're ready to push theirs back to the cloud. And as they do, when they push that back to the cloud, they're going to get conflicts. And the GitHub program, it's going to tell you that. It's going to identify them, that there are conflicts, and give you as much information as it can on where those are. There's another way to create a merge conflict from the web interface on GitHub. If you look up near a file, so like if you click on a file and you can see the contents of the file, there's a little pencil here for editing, and you can actually click on that pencil there and make edits to the file. You typically don't want to do that, especially in our labs, because if you do that, it bypasses all of the the testing that we've done. So you're really at risk of doing this, but it's there, it's available. Problem is if you do that, right? So if computer A does the clone, makes edits to the file, and then you come along or somebody else comes along on the github.com website, hits that pencil tool, edits that same file, and then returns to computer A, which does not have that edits, right? You've cloned it before you made the edits. Now you're going to have conflicts. So the github.com is effectively computer B in the previous slide. So you'll notice the conflicts when computer A tries to do a push, right after the edit tool has been used at the github.com. Right, so you got two different versions. The github.com is going to accept the the pencil edit version, but that's going to be different than your local computer. So when you go to push it, you're gonna see some problems there. So if we look at alternatives, how do we solve this problem here? There's a number of ways to do it. We're going to look at two ways. One of them is to delete the out of sync repository and then reclone it, right? So on your local machine, if there's a conflict, if you're not worried about the code on your machine, you can just delete that repository and start over again, reclone it, make changes, add, commit, push. The bad part about this is if you had work on your local repository, and most likely you did, otherwise you wouldn't had a merge conflict, then you're going to lose all of that work. If you're not worried about that, if you know what you did, then not an issue at all. This is really the simplest and the fast way to resolve it. But it requires you to, accept the fact that you're going to lose some work. If you know what it was and you can redo it very, very quickly, hopefully you were fresh when you wrote it and tried to push it and realized there was a conflict. You can go back in and make edits. And another thing you can do before you delete the out of scope repo is copy some, if you know where you made the changes, copy that source code to a temporary directory, go through the delete process, reclone it, and then you have a copy of this file that you edited that you could either cut and paste data into or copy the whole file over to, whatever works. But that allows you to maintain some of those programming statements that you had if they're minor. Another way to do it is actually go through it and manually resolve conflicts. The bad part about this is there's more source control work, and it takes you as a programmer to go through and visually look at each one of the conflicts and make a decision on what is the one that you want to be in effect, and remove one, or look at the combined data and make a new adjustment based on the two conflicts. But you got to go through it one by one, and that's the part that takes a little bit of time to do it. If there's only one conflict, not an issue at all. This is good in that it preserves all of the programming work that you've done. You're not just discarding it. So those are a couple of different ways, and we're going to step through a couple of those examples there. So solution one is deleting that local repository and then recloning it. So what you want to do is on that computer with the out of sync repository, identify which repository is out of sync. So you can execute the git status command on your terminal, note which files are modified. My suggestion is whatever files are modified, save them somewhere, put them off to the side in a temporary directory. You need to confirm that deleting the edits is acceptable. So if you're okay with it and you got a handle on it and you know that you're gonna lose that code until you go back into these files that you may have saved and copy code back into it, then that's what you're doing. You're basically acknowledging that you are going to delete those. You want to open these modified files in the Visual Studio Code, and then make that decision. Can you live with deleting the edits? Because once you proceed here, you can't undo it. It's gone for sure. So assuming that you're okay with deleting the edits, you've saved code somewhere else that you can cut and paste back in, or you can retype it, maybe one statement. Then you proceed with deleting that local repository. So you're going to actually move outside the repository with the cd command, right? Just go back up to the parent directory in front of the repository, whatever the path is. And you're going to delete the entire repository using this command right here, right? So the RM for remove, space, hyphen RF, this is going to recursively go through whatever your repository path is. You're going to replace this with the repository path, and that will remove it. And like we mentioned here, can't undo it. So just make sure you really want to remove that. And then just check that the repository was deleted. Just type that ls command right in the terminal, and you will no longer see the folder that had that repository in it. All right. Solution 2 is resolving the conflicts. So on the computer with the out of sync repo, the git push prints the command error. So when you're trying, you'll notice that when you try to do git push, and you're going to start getting some errors, right? Error, failed to push some references. You may first want to integrate remote changes before pushing again. So follow this advice, right? This is what you want to do using the git pull. So your next command is git pull, right? That's going to pull down the repository from the cloud. You have a local repository. You already know they're different. That's what the git push told you. And just make sure that there's no errors after you do that. And then you're going to look at the automatic merge failed. Should be there, and then just continue on in those next steps. So now we can start to identify where it is. You can use the git status on that terminal command. Note which files are modified, and you can edit the files and manually eliminate conflicts. You'll go through them one by one. For each file modified, open it in Visual Studio Code, find each conflict. They're going to be color coded, and they'll be marked with a whole bunch of less than signs, kind of a arrow to the left with the word head. And then you'll see what one file has, the exact statement from one file, the exact statement from another file will be underneath it. And then there'll be a kind of a closing footer with some, hexadecimal number on it that associates with the actual conflict. So there's a button down at the bottom to click, and that's to keep the version. Once you've gone through every one of the files that have been modified, there's more than one, you got to go through each one of them, follow this through, and if there are conflicts in more than one spot on the file, make sure you scroll through the whole file. There could be a section that has a header, a couple of lines, and then a footer. And then if you scroll down more, there may be another area in that same file. So you want to make sure you've addressed all of them. Deflict it, choose which one you want to keep. And then when you're all done, save the files, add, commit, and push as usual. And that should sync everything up. That's the best way. That's the best way to do it without losing any code. All right, so let's look at an example here. So we start off, and both computers, A and B, both do a git clone. All right, so now we got two computers. So if computer A takes this file sandwich.cc and adds a line in here, right? So we declare a string, a couple of strings in that file there, and then computer A proceeds to add, commit, and push or merge back with the cloud. So you have the git add sandwich.cc, git commit -m, put a your common statement in there for whatever the changes was for this version. We just use declare variables, and then do your git push, right? Since this is the first one, since we've cloned it, shouldn't have any issues on this one at all. So now the cloud is going to be aligned with this statement right here, right? string, protein, bread, and condiment. Now the programmer on computer B opens up the same file and makes a statement that's a little bit differently. They've declared the variable, but they're using different names, right? P, B, and C, rather than what was chosen by the first programmer. Nothing wrong with that. This programmer B proceeds to add, commit, and push. So they do their git add sandwich.cc, git commit -m with their message, and then their git push. And now you get some errors, warnings and errors, right? And this is what is going to be reflected if you get those git merge errors. It's going to tell you that there were some, failed to push it. So actually this didn't do anything. It did not push it at all. It's letting you know that, and it's giving you some information. And down here is about using the git push, and that's the part we're saying to follow this to ensure that the synchronization completes correctly. So now we're going to proceed on computer B to resolve the merge conflicts manually. So the next step is, after we did the git push and got the error, is do a git pull. That's going to pull that code that it found conflicts with from the cloud into your repository. It keeps them separate, right? They're separate instances, so to speak. And now you go into Visual Code, and you're going to see something like this, right? There's that head, right? There's that header, and this is kind of the footer with that hexadecimal number on it there. And what you'll see is one of the files line of code that differs from the other file's line of code. So everything up above here was all good. They were all the same. But when it got down to this line of code right here, we're starting to see differences, right? So this is where you resolve it, and you decide, looking at those right there, you can either pick one or edit, however you want to do it, and then just hit that resolve and merge editor. And then when you're all done, it's going to look something like this, right? And what I was mentioning before is just make sure you scroll down through the whole file. This is a short file. You can tell it ended right here. There could have been other conflicts down below. So there could be multiple conflicts. Make sure you address all of them. When you're all done, then those header, footer, conflict identifiers are gone. Your file is going to look like this. And just make sure you save that file when you're all done. And then do a git status. And your git status is going to let you know, that both of the files were modified. Here's what it is right here. And then no changes added to commit. So you need to go on and do now a git add sandwich cc, git commit -m, and then git push, right? And that will push, that will resolve the conflicts from computer B up to the cloud. But depending on, be aware, depending on how you resolve the conflict, computer A could be now have a merge conflict. So you might have to do, one of them you might have to, decide which computer is the correct one, and then maybe do step one on the other computer where you just delete the repository locally and reclone it, and that will align the computers A and B. So deleting or merging, deleting an out of sync repository. This potentially loses programming work edits. It does lose them, but like I said, you can temporarily put those in another file so that you can copy and paste back in. You have to do that manually. The merge saves a lot of work, but you need to go through and do all the merge work. So choose whichever is less of a setback, and it's really going to depend on how, how broad the conflicts are. If you have a very large repository, and there's a lot of conflicts, you're probably going to want to go through and do the merging, because you're going to need to go through them one by one and figure out which is the right one. Best thing to do is don't get yourself into that, and always keep the cloud GitHub as the authoritative source of your code. If you're always working, and when you sit down to do some work, right, do a clone, edit, push, and when you're done doing your work for that time, push it back up. Right, the next time you come along, you could almost delete that and start over again. Clone, edit, push. Remember that: clone, edit, push. And if you just make sure that two people aren't doing edits at the same time, then you should be okay with that. So preventing those merge conflicts, ounce of prevention is worth a pound of cure. It's better to just avoid the conflicts than spend time fixing them. Only work on one computer at a time. And before leaving that computer, do that add, commit, push. Arriving at a different computer, clone or git pull, do your work, and then add, commit, push right when you're done, right? So I would always get in the habit of cloning or polling, do your work, push. Cloning or polling, do your work, push. If you clone or poll and do your work and you don't push, and you come along later on, or that other computer comes along, that's where you run the risk of those merge conflicts. Recommend do not use that GitHub pencil tool. It's available for you to use, but you can certainly get in trouble for it on these merge conflicts, and it potentially could affect what you saw on your unit testing, and other tools that we've built for you in the lab. So highly recommend not using that at all. All right, constant functions. Constant functions. So let's look at the principle of least privilege, which only grants access that is truly necessary based on a need to know basis. This is real evident in our Apple iOS operating systems, the Android apps. An example of that is your location. Right? You can selectively, very selectively, turn that off so that the application either absolutely does not have access to it. It only has access to it when you're in the application. There's a couple of different levels that you can respond to on that, right? So that's a user granting access to that. It's a security control. This prevents the bugs from causing any undue harm in the program, right? That's on the programmer side. And on the user side, it prevents any spyware, any other programs from attacking vulnerabilities in a application or exploiting vulnerabilities. It really does a good job to prevent that. All right, so const, C-O-N-S-T, this is another keyword. We've seen this a couple of times already through our lectures. In general, it just means it's short for the word constants, and we put it in front of a identifier, like a variable. But by putting this in there, once we put the qualifier const in front of the variable, then that signifies that it should not change, and any subsequent code that tries to change it, we will get a compiler error, right? And that's that least privilege, right? We're building some security around that variable. We need the variable to hold a value, but we don't want it to change. And so we don't want other programmers to change it. So by using this, It just prevents the compiler from going any further if a programmer does try to make a change. Maybe it's you trying to make the change and you forgot that it was a constant. It's going to kind of stop you and notify you right in your tracks when you're compiling it. So we also have constant references, right? A variable is a reference to an object. We use those a lot. References cannot be used to change the object. So if we're using a constant reference, then the reference can't change the object. We can access it, right? Use it as an accessor, read from it, but we can't write to it. And then we also can have constant member functions in those classes. And the function cannot change any member variable. So we do that on purpose to prevent ourselves as programmers from trying to change anything in there, or and prevent any users of our class from changing any variables. So typically we see that in accessors, right? Like an accessor member function where we just want to read the value of something. Right? There's no reason to be changing anything. We're gonna access a variable and return it. So it's good to qualify those as constant member functions, and that prevents it from happening. The constant keyword is a variable that cannot be modified. And it grants that read-only access to an object, and it's appropriate for loops and functions that have no business modifying the object. It uses this principle of least privilege, and it prevents modifying through the reference by accident. So if we have a variable, maybe identified as B, and we've assigned some value to it, 7, maybe an integer variable, and we create some references. Reference 1 that points to that, 2 and 3, they all point to that. If these are not qualified as constant references, then I can actually, through this variable here, this reference, I can change this 7. I can change it to another value, say 8. And if I do that, then B is now going to be impacted by that. Reference 2 and reference 3 is going to be impacted by that. And that may not be what we want. If we have all of these as constant references, then the only thing that can change this is B, assuming that it wasn't set up as a constant integer itself, right? So that limits that, right? It's that least privilege. We're building some security around this variable, so we're allowing other variables to look at it and reference it, but not change it. So just a review on the L value reference to a constant. The syntax is there's that keyword constant, whatever the reference type is, maybe an integer, and then a ampersand, and that's the token for a reference to an object, right? We're setting that up as a reference. So reference to an object that may not be modified. That's how you would set it up right there. You'll get a compiler error if in your subsequent code you do try to make edits to that. The constant reference can refer to a non-constant L value. This is much stricter. A non-constant reference cannot refer to a constant reference. This would break that protection. So here's some example code over here. So we start off, here's that maybe an integer, variable name identifier is X. We initialize it to a value of 3, right? Then we create a integer reference. That's what that ampersand is. We give it a name, reference 1, and we classify it as a constant. So it's a constant integer reference with the name ref_1. And this is what it is referencing, right? It's referencing whatever the value of X is, okay? Whatever the contents of X is. It's actually referencing the address, the memory location of X, right? So we'll actually get the, um, the, the, the address of that. So if you now try to create another, just a integer reference, not a constant integer, but an integer reference by the name of reference underscore 2, and have it reference 1, which is a constant, that's where you're going to get the compiler error, right? This is this third bullet down here that's not acceptable. You can make changes to X directly, that's okay, but you cannot make changes to the reference 1, right? You'd have to comment this out in order for this code to compile, but assuming you got rid of that and tried to compile it again, you would also get a new compile error on this line right here, because this right here, this identifier is a constant and you cannot make changes to it. So it's not going to allow you to do that. You can read from it, right? You can read whatever reference 1 is, right? It points to this right here. You can actually see what that value is, 3, but you can't change it. The only thing that could change it is the X based on the code here. All right, constant in for loops. Another good practice. For loop variable is a reference variable. So the best practice is to declare for each variable reference constant, right? So whatever that variable is in your for each loop that you create, declare it as a reference constant. That's the best practice. All right, so here's the unsafe way of doing it. Assuming that we have a vector of doubles, right? We've initialized that. So scores is our vector name. We got a whole bunch of double values in there. Now, if we want to build a for loop to iterate through those, right? We're going to iterate through this scores here. And for each iteration, we're going to pull out whatever this value is, 91.0, and assign it to this variable right here, score. Now, right here, we declared this as a double reference to whatever this is right here. Now, all we're doing is just outputting it, right? So we're only reading from it. So there's really no harm done in the code that we see right here, but potentially you could write to that. You could make edits to this variable right here that would in turn change this value right here in the first iteration, or this value in the second iteration, and so on and so forth. All right, so that's where the potential is. You could actually change the values in that original vector, right? So that's a little unsafe. The safer way of doing it is to preserve that level of security and add the word constant out in front of that, right? So now we have a constant double reference variable named score. It's going to iterate through here. 91.1 will come into this value. If we tried at all to have another statement down here where we were going to change the value of score, that will give us a compiler error because we put that word constant in there. And that's good protection, right? Unless you know that you want to make changes to this original vector right here, it's better to build the security around it. Use that constant, and it'll prevent that from happening. All right, constant member function. Recall that member function is inside of a class, and by default, member functions are not constant. You have to specifically annotate the constant. You want to mark a function constant by writing the constant, C-O-N-S-T, keyword after the parentheses in the prototype and the declaration, right? So both of them must match. The constant member function cannot modify any of the data members. That's the purpose of putting that in there. Same concept as that loop there is it prevents modification of variables. And when you're designing your code and laying it out, if you know you don't want to you're not going to be making changes, put that constant in there, and that'll prevent, you know, errors. Maybe you put your code down for a couple of weeks, you pick it back up, you forgot about that, and you're looking at a function and you start making changes to some of the data members, and that wasn't the intent of the function. You know, if you didn't have this constant in here, you're not going to get any errors. It's going to proceed, won't get any compiler warnings, and you could introduce some logic errors. So this will putting the constant keyword in the functions will prevent that. And looking at a example called scoreboard entry. So we have our header file and our code file. On the header file, we have our class scoreboard entry. In the public, we have two constructors, a scoreboard entry with no parameters, a scoreboard entry with a different signature. It's got a couple parameters, and then we have some member functions, and this is just the prototype, and another one here, and then down in our private area, we have a couple of member variables, right? So the constant member functions is right here. So right after the name of the function, parentheses, after the parentheses, put the word constant. That's where it's going to go. And that will prevent that function on the definition of the function from making any changes to any of these member variables here. All right, so on our CC file, here is the definition of the scoreboard entry constructor. The one that has 0 parameters is the signature. There's the other one that has, looks like 2 parameters as a signature. And then we get down into the definition of those functions. And again, you have that same constant right after the very last parenthesis of the function. And we aren't making any changes. All we're doing is reading, right? We're accessing this name variable right here. That's all we're doing in that function. We're not making any changes. So put that constant there. For the score, constant here, all we're doing is reading from the score variable. That's our member variable score. We're reading from it, returning it as an integer, not making any changes. It's best to put that there. Right, so these are both accessors. You probably will always want to use a constant qualifier for any of the accessors if that's all you're doing is just reading values. There should be no reason to make changes. Put that constant in there, provides a little bit level of protection there. So the purpose of the constant member functions is the principle of least privilege, and it only gives permission to modify those data members to functions that actually need to do that. It also prevents logic errors. Those member functions modifies variables by mistake. And the caller, they do not expect data members to change. So it's best to use that constant member function. And the best practice is every member function is constant unless it has a specific need to modify a data member. So you can almost use that as a, you know, as a go-to or a basis. Use it for every single function. If you build a function where you're actually modifying data members, then just remove it, right? And you're removing it because there you have a purpose to do that, right? So those constructors most always initialize data members. So they don't want to be, you never want to have a constructor being a constant because that's where you're setting up and writing to those data members. Accessors, on the other hand, almost always never make any changes. They shouldn't be making changes, so they're always going to be the constant. And just the last slide here, examples of some constant member functions that we've seen so far is vector and the color RGB that has some accessors for red, green, and blue, right? Those are going to be constant member functions because the accessors aren't changing anything. All right, so that completes our lecture for tonight. Appreciate you guys all hanging in there. And remember to come prepared on Thursday. I'm sorry, Wednesday of this week with any questions for the review. Thanks, everybody. Appreciate it.